So, let us see the properties of these aldehydes and ketones. Under that, one property we have seen, that is nucleophilic addition reactions with like HCN, sodium bisulfite, addition of Grignard reagent, water, ammonia, alcohol, and so on. Now, at the end we have seen ammonia adds to the carbonyl compounds and gives a very unstable compound, because the ammonia has got very low boiling point. Slight temperature increases also, the ammonia will come out and gives the original starting material. That is a bouncing back type of the reaction. However, if that ammonia is having some group like hydroxy group or a NH2 group or benzene group, then the boiling point of the compound will be more. So, therefore, outcoming property of that ammonia will be less. So, therefore, we have the stable products formation in the case of Y substituted ammonia. All that reactions slightly deviates also from the nucleophilic addition reaction, and then we will have some elimination of water, and the reaction leads to give the condensation type of the reaction. Let us see how the reaction mechanism goes in general first. So, a carbonyl compound will react with this NH2OH. As I said, the lone pair of the N will attack on the carbon, followed by a proton will attack, or the mechanism if you see, then you can have like this NH2 plus and the Y. So, the O will have a minus, then one hydrogen transfers here. So, we will get a NH, Y and the OH. Now, this OH and H, instead of this big group coming out, this OH and the hydrogen will go out as a water molecule, and then gives the H2O liberation is, you can say, minus of H2O or dehydration taking place, a double bond is formed. So, finally, what you will get from this is a carbonyl compound directly makes a double bond with the nitrogen. So, here HOH removal makes a double bond, then the H. So, this type of reaction overall we can also make a box like this. The O and the H2, if it is removed, you will get the answer. That is what we say this reaction is a condensation. Condensation means water formation. Even we say oftenly a formation of water that is from the clouds. A rain we describe as a condensation. So, here also from these two molecules, a carbonyl compound and a NH2Y eliminates a water molecule minus of H2O. Directly you can write this equation. However, the reaction has the clear reactions. One is the nucleophile adds and the proton exchanges. Up to this is the nucleophilic addition reaction is over. So, this product undergoes now elimination reaction, right. So, therefore, the mechanism of this reaction is first nucleophilic addition followed by the elimination mechanism. Net together, however, we are calling as a condensation. As such, there is no condensation reaction. It is made up of with the two different reactions. One is nucleophilic addition followed by elimination. If somebody claims that this is the mechanism of the reaction, that is that side hydrogen, two hydrogen coming, this side O coming and removed as a water, that itself is the mechanism, means that is wrong, because it is a nucleophile adding followed by the proton adding, that is the nucleophilic addition, then elimination. It is a two reactions together we are claiming as a condensation reaction. Now, in the case of ammonia, we are getting a reversible reaction, but if Y is there, that means a new group, if it is there, a bigger group is there, it is giving a successive reaction that gives to a final product, that is a condensed products are forming. Now, we have 5 different examples are there for this type of the Y. As a Y goes on change, there are 5 beautiful examples are there. All these examples are having some synthetic applications and all that reactions we will see. Let us take the first example of this category. If NH2Y is equals to NH2OH, that means the Y group is OH. You can say water containing ammonia. You can also say hydroxy group containing, but a water containing ammonia. This is called a hydroxy ammonia, commonly known as hydroxylamine. Hydroxylamine. This is as such a liquid, very unstable compound. Many times in the market, some HCl, concentrated HCl is added and it is converted into the salt, that is hydroxylamine hydrochloride. Just like ammonia, when you add concentrated HCl, ammonium chloride solid is formed. Like that, this compound also, this unstable compound, maybe some oxidation, decomposition is taking place. Therefore, concentrated HCl, when you add, it will become its hydrochloride, which is quite stable. So, in the market, it is available in the form of hydroxylamine hydrochloride. So, when you add that reagent, HCl is extra, the compound in the form of salt. So, the reactivity will be less. So, in such a case, we add some base like sodium acetate to take away that HCl. You get this compound. So, when this compound is treated with a carbonyl compound, like for example, acetone, let us take, okay. So, acetone is a CH3CH3, and this reagent I will add and show the reaction. So, I said there is a shortcut mechanism, that is H2 from this side O. This is not the real mechanism, but still a box may be shown and to get instantly the answer. So, the answers are now acetone will be as it is, but the N will become now OH attached to this one. This is called, you call the name of the compound, whatever it is. You can say acetone, common name, or dimethyl ketone, common name, or propanone, you can say propanone, and then say this hydroxylamine products are called oximes. So, this answer is now you call it as the acetone oxime, or common name, the IUPAC name, that is propanone oxime. So, a question may be asked, any carbonyl compound, when you add hydroxylamine, the products are known as oximes, right? Then similarly, if the reagent is NH2NH2, that is ammonia containing ammonia, this is called hydrazine. The hydrazine reacts with acetone, and acetone, if it is written like this, a box mechanism may be shown to get the answer. So, acetone attached with the NH2. These products are called, this is hydrazine. So, call the name of the acetone, okay. Then you say hydrazone. Z-I-N-E is there in the reagent name, has become now Z-O-N-E. So, acetone hydrazone is formed, right. So, it is a condensation reaction gives, and all these products, there are 5 reactions are there, all the products are beautifully crystalline compounds. So, immediately when you add this reagent, the carbonyl compound converts into a crystalline compound. So, they are all working as a test salts. Then we have another reagent, NH2NH, a benzene ring. This is known as phenylhydrazine. Phenylhydrazine. If acetone is taken, added this NH2, NH phenyl, you can write pH and leave it also. So, the answer will be acetone phenylhydrazone. This is called dash dash. Then only thing is the part which changes is a gyne, Z-I-N-E changes into Z-O-N-E. So, the changed part I have represented clearly. First say the name of the carbonyl compound. To take benzaldehyde, say benzaldehyde. In this case, acetone. Reagent is phenylhydrazine. Change it to the, in the nomenclature, phenylhydrazone. The fourth reagent is NH2NH. There is a phenyl ring, but this phenyl has 2 nitro groups, where specifically at a 2nd and 4th position. Therefore, it is called 2,4-DNP, commonly known as DNP. It stands for 2,4-dinitrophenylhydrazine. 2,4-dinitrophenylhydrazine. phenylhydrazine. It's an extension to this one. Now, the similar reaction between the acetone and the 2,4-dinitrophenylhydrazine, if I write. So, answer will be the same type of the answer will come. Acetone with 2,4-dinitrophenyl. This is called again, the reagent ends with Z-I-N-E. The reagent name is 2,4-dinitrophenylhydrazine. The answer name will be the compound name, carbonyl compound name, then the name of the reagent ending with the Z-O-N-E. All these names are commonized, and then we are having the similar type of the nomenclature. Lastly, we have one more reagent. The reagent is NH2NH-CONH2. This particular group, if you call, this is nothing but the urea. NH2CONH2 is called urea. Now, urea containing ammonia we have taken. This reagent is called semi-carbazide. Initially it was called ZIDE, but later it is systematized. Again, this is also called semi-carbazine. The reagent is called semi-carbazine. Similarly, a carbonyl compound reacts and gives the acetone. Let us take acetone with semi-carbazine. So, NH is over, then you write the urea part now, NHCONH2. This is also called dash dash with Z-O-N-E. First dash is the name of the carbonyl compound, second dash will be the name of the compound reagent, semi-carbazine will become into Z-O-N-E, zone. This is Z-O-N-E, zone. So, all these derivatives, as I said, they are all solid derivatives, but in the case of fourth one, that is 2,4-DNP, the reagent itself already solid, it is in the form of the orange to red color is there. So, this it is solid means it is dissolved in the, they are all liquids, otherwise this and this all are these liquids. This is a solid one. So, the solid is dissolved in the minimum quantity of ethyl alcohol and the reagent is prepared, kept ready, and this reagent in alcoholic solution added to the carbonyl compounds. Fortunately, most of the carbonyl compounds are liquids. So, the moment you add this the alcoholic solution, immediately you will get a precipitate. Except formaldehyde, I said it is gas dissolved in the water, aqueous solution is available. In the last one, benzophenone, that is the one of the classical example I said at the end, 2 phenyls containing ketone, which is solid. In that case also you have to dissolve in the minimum quantity of alcohol, then add this alcoholic solution of this 2,4-DNP, immediately you will get a red color precipitate. So, this is the only the one red color precipitate, rest are all white color, these are all white color precipitates. The last one also white. The only the 2,4-DNP derivative is the red colored one. So, therefore, in this case, the reagent is also in fact orange colored one. These are all white colored and giving the derivatives also white color. But this is the one orange color, orange to red will be there, and here also depending upon the aliphatic and aromatic. Aromatic will give little more darker color because of the conjugation and all that. So, either you get orange or red, but you will get a beautiful red color crystalline compound. If necessary, slightly warm it after adding. Sometimes without warming also you will get it, but sometimes depending upon the compound reactivity, you may need to slightly warm it, you will get a beautiful red color precipitate. So, these derivatives are very much useful in the different types of the synthetic applications and all that. A few applications wherever it is necessary we will take. So, let us take some applications of oximes. The oximes are the products when hydroxyl amine is added to the carbonyl compound, their derivatives are called oximes. So, the oximes have two applications. One is dehydration of oximes, dehydration of especially aldoximes. So, any aldehyde like for example acetaldehyde is taken. Acetaldehyde I have taken as an example, but acetaldehyde let us first convert into the oxime. Okay. So, oxime conversion is this H2 and O will be removed. You will get acetaldehyde oxime, may also called a little slight variation. You must say actually acetaldehyde oxime, but we have some concession in calling acetaldoxime. In the case of aldehydes, you have this, we have here see acetaldehyde, the hide is gone. So, acetaldoxime, that procedure is there in adopting this type of the nomenclature. So, this acetaldoxime, when you heat it with a dehydrating agent, especially like P2O5, such reagents will take away this HOH like this. So, minus of H2O, probably this P2O5 will become into corresponding acid, but the our compound will become into CH3, C triple bond N. Right? This is a cyanide, alkyl cyanide or nitrile. Cyanides are formed. So, we have a beautiful exercise previously in IIT also asked, how do you convert benzaldehyde into a nitrile, benzonitrile it is called. Two-step reaction it is. First you add hydroxylamine, make benzaldehyde oxime, then add some dehydrating agent like P2O5, or you can also add acetic anhydride AC2O. Even this works as a dehydrating agent. In this case acetic anhydride take that water becomes into acetic acid. So, our compound undergoing a loss of water, that water is transferred to the acetic anhydride, this becomes into the acetic acid. So, benzaldehyde to benzonitrile, or you can say phenyl cyanide, CN with phenyl, radical function nomenclature. It is a function nomenclature, benzonitrile is their nomenclature. Now, this compound how do you convert means, in the step 1 you add hydroxylamine, right. So, benzaldehyde will become into benzaldoxime. Then you add the either acetic anhydride or P2O5, you will get the cyanide formation. So, benzaldehyde to this one. Another method is also you can oxidize to benzaldehyde into oxidation to give the benzoic acid. Make benzamide by adding ammonia distillation, benzamide comes. Even benzamide also with P2O5 will become into the cyanide. So, that will become a 3 steps. Now, in this only is 2 steps, oxime formation, dehydration will give the cyanides. Similarly, oximes have one more application, especially the ketoximes, dehydration of aldoximes. There is a name reaction called Beckmann rearrangement. Beckmann rearrangement of ketoximes. So, aldoximes undergo dehydration, whereas ketoximes undergo rearrangement reaction. So, I will take here a ketoxime like an acetone you take first, the convert into the oxime by adding the NH2OH. So, what you will get is acetone oxime is formed, acetone oxime, a ketone corresponding oxime. This one when you add this H plus, that is a strong acid, then the H plus, the overall mechanism will be like this. H plus attacks on the OH, O will become positive, this H2O will come out. So, this methyl will change to the nitrogen, the water will come back and give say OH. So, temporarily what you will get is the OH will come, methyl will go there. So, okay, I will write like this. So, this methyl changed to there, right. So, this methyl as it is. So, during this reaction what happened? A protonation, the followed by removal of water, this methyl will go there, water will come back and leave the proton back. So, the OH will settle. This is the enol. So, therefore, it tautomerizes to become into the ketone. So, therefore, what is formed is CH3CO NH with methyl. So, this methyl was actually on the carbon gone to the N. So a shuffling, internal shuffling of the compound took place. This is called a rearrangement, suggested by this scientist called Beckmann rearrangement. A beautiful rearrangement it is. It has got a lot of discussion on the mechanism, application in the synthetic chemistry and so on. A slight mechanism you can also see here. With reference to the mechanism of this Beckmann rearrangement, it is a rearrangement, not the reaction, it is a rearrangement. Let it be clear. It is a rearrangement, Beckmann's rearrangement. In this rearrangement, I am taking now, unlike the previous example, we are taking now two different alkyl groups. One is CH3, that is methyl group, the other one is phenyl. This type of ketone is now, it is said to be a unsymmetrical type of the ketone. One side one alkyl, another side another type of the group is there. They are not identical. You can take identical. In the case of identical, discussion will become easy. So let us have a little more complicated type of the mechanism. In this case, so first make the oxime, right? So the product will be a methyl with a N and the phenyl. On the N now, if you carefully see, there is a lone pair will be there and there is a OH will be there, right? Nitrogen is a trivalent, if a double bond is there, therefore one OH and the lone pair. Now, there is another compound which is also exists simultaneously. This go on change, this lone pair is a cloud, so it can diffuse this side and the OH may go that side. So therefore, there is one more oxime, the OH may come like this. Now these two oximes are not same, they are a sort of geometric isomers, but not exactly geometric also, because geometric isomers will not undergo conversion. They are all, these two are dynamically going on, even at low temperature also the conversion is very easy. Therefore, with a minimum energy this cloud will go that. So therefore, even one if you prepare pure compound also, within no time it converts. So always there is a mixture existed. But these two are not identical. They are two different compounds exist in the equilibrium. A dynamic equilibrium will be there. However, now with reference to this phenyl and the OH, I call this a phenyl, anti-phenyl and hydroxy. We have to say this specifically, you have to say with reference to the phenyl it is anti. Here with reference to the CH3 it is anti. Or with reference to the methyl it is syn. So one is said to be a syn, the other one is said to be anti. If I want to say with reference to the phenyl, phenyl methyl, this is anti. Phenyl anti. Anti-oxime. Oxime of dash. The dash is acetophenone, whatever the name if you give, acetophenone, oxime of phenyl anti. Here phenyl syn it is. So you are specifically mentioning to which group it is syn. So to the phenyl it is syn and then oxime of acetophenone. There are two compounds. Both the compounds undergo rearrangement, but in this case, unlike the previous examples like pinocol, pinocolone type, when two alkyl groups, different groups are having a possibility of shifting, there the order was the alkyl group shifts better than the hydrogen, better than the phenyl group. Here it is not like that. Whichever is the opposite, that is anti, will migrate. So in this case, to the OH, methyl is opposite. Therefore, so methyl migrates here, a temporary compound like this is formed. So methyl is migrated and the OH goes there. This is however temporary, it undergoes a tautomerization. So the final compound will be the phenyl C double bond O NHC. N-alkyl amides are formed. Okay, that is retaining its structure. Let us have, it is somewhat more easy to follow. So the OH has come here, the phenyl has gone there, right? Then the methyl original one. This undergoes a tautomerism. Then you will get a CH3 CO NH phenyl. Call it as a first one as a N-methyl benzamide. this is a N-phenyl acetamide. So these two are the final answers. Both are amides. N-alkyl amides will be the answer. I have taken only one compound. You are getting two answers. How it is possible means, after reacting with hydroxylamine, what comes is called an oxime. In the case of ketones, if it is unsymmetrical, there are two different types of the oximes are coming. If two methyls are same, if both the sides are phenyls, then it will give only one oxime. There was one question, which of the following carbonyl compounds will give single type of oxime? That means you verify whether the taken ketone is symmetrical or not. All aldehydes except formaldehyde will give only one type. Except formaldehyde will give the two different types. Formaldehyde will give the only single type, and the symmetrical ketones also will give the single type of oximes. This different types are there. Unidentical groups are there. So therefore, you are going to get the two different oximes which are in equilibrium. Therefore, you cannot prepare only one type of the compound. They are going on exchanging. Therefore, two answers are inevitable. So sometimes phenyl migrates when phenyl is opposite. Sometimes methyl migrates when methyl is migrate. Therefore, two types of answers are coming. Wonderful examples are there. Go on, take the different types of the both alkyls you can take, both phenyls, aromatic you can take, one aliphatic, one aromatic you take, different types of the examples will give. However, we have one classical example like a cyclohexanone at the NH2OH. Then what happened, this O and the H2 will go out as a water, an oxime is formed. This oxime, call it as a cyclohexanone oxime. Then this is treated with the strong acid like sulfuric acid. The catalyst is here for the catalyzing the reaction is the strong acid, that is concentrated sulfuric acid is the classical example. But however, not necessarily concentrated sulfuric acid. You can have any Lewis acid like PCl5, thionyl chloride, aluminum chloride, BF3 and so on also can be utilized. Even acetic anhydride can give the reaction. Now this the proton will attack and the water is lost. One of the group which is opposite, if the OH is this side, if the OH is that side, this group will migrate and you will get a 7-membered ring formation takes place. That is N with the hydrogen and this side you will get a ketone. This is called an amide containing a 6 carbons called a 6 carbon oic acid called caproic acid with a amino. Capro is a lactam, it is. So cyclic amides are called lactam, so it is caproic acid lactam, so it is called caprolactam. So a caprolactam comes. Lactam means cyclic amide. Now this amide, if you hydrolyze with the dilute acids, you will get the really a carboxylic acid containing the amino group. One side COOH acid, the other side amino. So the name of this compound will be the 6-amino caproic acid or 6-amino hexanoic acid. This compound on polymerization we have synthetically a nylon 6 comes, that is 6 carbon oic acid is involved. So commercially we have retained that 6 and the compound polymer is known as nylon 6. You know how beautifully the nylon 6 polymers are having synthetic applications in the industry. So how you prepare nylon means generally from the phenol reduced from cyclohexanol oxidized to cyclohexanone. Hexanone is converted to oxime, cyclohexanone oxime. This on Beckmann rearrangement gives the alkyl group opposite to OH is this ring residue. This will cut here and jumps to here and makes a 7-membered ring. That's what a 6-membered ring has become into 7-membered ring expansion taking place. It is nothing but the same mechanism of the Beckmann rearrangement. This 7-membered ring, on opening you will get a 6 carbon oic acid with amino, which on polymerization in acidic medium an amide, polyamide is formed, that is nothing but the nylon 6. This is the one synthetic application, but the Beckmann rearrangement really has got so many the synthetic applications and variety of N-alkyl amides are prepared from the Beckmann rearrangement. applications of hydrogens. So, when a carbonyl compound like acetone, when treated with the hydrazine, so what you will get is called what? Hydrogen. This hydrogen has one further reaction. If acetone is added further, then treated, then the other side also reaction takes place. Already one side acetone condensed, now other side N also involves in the condensation like this. The final product is called a dash azine. Dash is the name of the carbonyl compound, you call it as a acetone azine. That means you can add a 1:1 ratio, then you get hydrogen, then one more mole of acetone if you add, otherwise you take 2:1 ratio and then heat it. Then 2 moles of acetone, 1 mole of this one, that is excess of acetone if you add, directly you will get the azines. Azines have got some applications, even synthetic cyclic azides like this. For example, instead of 2 acetones, this side one, that side one, you can write like this. See, a carbonyl compound. This is one acetone, isn't it? You can have one more acetone here. Okay, like this. So, this is one acetone, this is one acetone. When I add this hydrazine, so a condensation leads to give the now 4 carbons and 2 nitrogens, beautiful a 6-membered ring is formed. This is the answer, isn't it? So, if you see 2 acetones, if separately taken, you will get azine. But if it is attached, acetone and acetone, it is called diacetone. The diacetone when add if you have, you will get a cyclic ring, that is a heterocyclic rings are formed. So, this type of beautiful synthetic applications are there for the azines. Azines have very good medicinal chemistry applications, and synthetic rings are also having the hetero type of the atoms also have got some attraction in the synthetic chemistry. We have one more application for these hydrogens. For example, if I take acetone, you add hydrazine, what you will get is called acetone hydrogen. This acetone hydrogen is taken in a flask where there is no blast of air. Better you close it with fill it with nitrogen atmosphere, heat it with a strong base, and very strongly you have to heat it. In presence of a strong base, if you heat it, it decomposes into 3 pieces like this. This is our carbonyl compound, N2 gas will come out. Hydrogen gas is adjusted here because valency will not permit. So, what you will get is a CH2 with C with N2 liberation. But there should not be any nascent oxygen or even oxygen in the flask. If oxygen is there, that oxygen will come again, you will get back the acetone. So, in a reducing atmosphere, if you heat it with a strong base, many times the KOH and heat it strongly, or ethanol and ethoxide combination, that is 1:1 ratio of ethanol and a sodium salt of ethanol. This also works as a very good strong base combination. Ethoxide and ethanol mixture, add it and heat it strongly, then this compound is converted to this one. What is this? It is an alkane, right? So, therefore, the net reaction is how you prepare the alkane, that is the propane from the propanone, means it is a total reduction of CO in a strong basic medium. In acidic medium, we have such a type of reduction, that is Clemmensen reduction, concentrated HCl zinc amalgam using. Now, this is in strong base. Make hydrogen in a strong base we are reducing. So, if acid sensitive groups are there, this type of reducing in the basic medium will be a wonderful application. The total reaction from here to here, that is converting into hydrogen and then heating with the base, total net reaction is called Wolff-Kishner reduction. Wolff-Kishner reduction. Wolff-Kishner reduction. This is not Wolff rearrangement or Wolff-Kishner reduction. In this reduction, the carbonyl compounds are first converted into hydrogens. The hydrogens are heated with a strong base, they are converted to alkane. So, net conversion is a carbonyl compound is converted to alkane, that is the total CO. If hydrogen nickel is added, it will become alcohol. Then the further reduction will be slightly difficult. But here in one step only, that is no doubt 2 steps, but in one reaction, that is otherwise in a Wolff-Kishner reduction, the carbonyl group is totally reduced to the corresponding alkanes will come in this reduction. This is known as Wolff-Kishner reduction. This is also one of the application for the hydrogens. Applications of this 2,4-DNP derivatives. This is also one of the important point. The 2,4-DNP as a NH2NH has got a ring. In the ring we have the 2 nitro groups. What exactly the phenyl ring role and this nitro groups means? There are 2 lone pairs are there in the nitrogen. As I said, with carbonyl compound, the overall reaction involves the first nucleophile attack. There are 2 sites are there, a lone pair and the nitrogen in lone pair. If this is not there, either one can attack. But because this ring is there, this ring itself is a -M group. So therefore, the lone pair will be withdrawn. So therefore, only one will be attacking, but not this one. This is the one reason. And that too, we have 2 nitro groups. What these nitro groups are doing means, the nitro group, if you write its total structure, NO will withdraw the electrons and this double bond will be pulled, and then this pulling will become easy. So therefore, further the nitro groups are helping. Nitro group is also -M. So -M attached to -M, the two nitro groups at ortho and para. If the nitro is at meta position, only -I effect influences. But if the suitability of this nitro group at 2nd and 4th position, so 2 -M groups are there. So and that too suitability. So a -M benzene is a -M group having a 2 -M groups and that too positionally suitable groups. Therefore, the total reactivity, that is basicity of this lone pair is gone. So only one side attack, pure single answer will come, and that type of the single answer coming has got some applications in the melting point checking and so on. So therefore, what is the significance of this phenyl or the nitro groups means, they will not make this lone pair to attack. It is totally one side deactivated. So only one nitrogen will attack. That is the significance. Similarly, we have in the semi-carbogens also, we have 2 NH2 function, NH2, NH, C double bond O and NH2. Now here also there is one lone pair, here is also lone. In the hydrogen NH2, NH2, both the sides are attacking. Now to carbonyl compound, will this attack or will this attack? If the question comes up, the second one never attacks, only this will attack. The reason is, this is the amino group attached with the nitrogen, the small -I is influencing, but this lone pair cannot have any -M effect. Moreover, it may show +M but not -M. So therefore, this NH group will indirectly only -I influence, but not the -M influence. Here, this lone pair is withdrawn by the carbonyl group. So this NH2 has got a -M group linked. So this reactivity is totally withdrawn. Again, this type of the reaction takes place. So therefore, a carbonyl compound reacting with this side one structure, this side one structure, or both reacts or both not reacts, like that 3-4 options are there. Right option is always NH2 attached to N only condenses, NH2 attached to CO, basically it is an amide, it is right. So the amides will not react, only amines will undergo condensation. In fact, a carbonyl compounds can undergo condensation with the aniline or such type of compound. The products are called Schiff bases. Like that here also, some substituted ammonias, they condense the corresponding products, all they are called condensation products. This is the last variety of the reagent, that is semi-carbazide or semi-carbazine. The products are called semi-carbogens. In this case, we have to remember only NH2 attached to N condenses, but not the other side NH2 or NH2 specific. I may write this side, that side. But see that NH2 attached to CO reacts. I can write the reagent like this. Right, left is not the criteria, right? isn't it? NH2 this side, CO, NH and the NH2. Now, which condenses means, if you remember, right side, left side condenses are said means left side. Is it condensed? No, this will condense now. Because I said a lone pair attached with the nitrogen condense. A lone pair attached with a carbonyl compound is in minus M effect. This will not condense, only this condense. So, right and left is not the criteria. NH2 attached with the CO, NH2 attached with the benzene, they have a minus M groups, therefore they will not condense. Only then, probably if a methyl is there, for example, instead of this phenyl, if a CH3 is there, then this lone pair would have become more reactive than the ordinary NH2. That is the concept here.